to everyone for coming along. As you're aware, VANZ is sort of here for you, and so this session, it's the awareness day, so I'm just going to give it an overview of some of the condition monitoring technologies, the reliability, sort of the idea behind reliability, more detail on the vibration side of things, since this is the Vibrations Association. But as I go through this presentation, if you have any questions, if you have any dispute with what I say, any comments, anything you'd like to reflect on, that's going on in your plant, feel free to pop your hand up. Sometimes it's during those discussions where we get the, the best information for everyone. So anyway, without any further ado, I'll get started. So as I mentioned, my discussion is about vibration, condition monitoring and reliability improvements. And I guess the main theme that I want to get across today is the idea that condition monitoring by itself is very important, very useful way to find out the health of your equipment, and you can plan maintenance around it. You can do a lot of things with that. But the real focus should be on improving reliability. And knowing what the condition of the equipment is improves the plant reliability because you don't have the breakdowns. But when you consider, on an equipment by equipment basis, the actual reliability of the equipment, there's a lot we can do to improve that reliability, which then means the plant's more reliable. So I'll just briefly introduce some of the condition monitoring technologies, dwell a little bit on vibration, then talk a little bit more about, well, reliability improvement, or defect elimination is sort of a better term for the bigger picture of all of this. So, now I know some of you have been in this industry for a long time and some of you are newer to it. But the fact is that whatever our role is and whatever our, our level of experience and so on, we really have a great opportunity for the company where you work. And that is that by doing all these things we're about to talk about, and that the vendors are out there to help you be equipped to do, and the other speakers and so on, we can increase the availability of the plant, and we can reduce the amount of unplanned downtime and increase the capacity of the plant or facility, or whatever it is you run, and decrease the amount of planned downtime as well. So, a lot of people start from a position to say, well, we've got all this planned downtime, which we must have, and then what time is remaining, we can operate the plant and, run the facility, whatever we're doing. But by improving reliability and really taking a sharp look at how the plant's being operated, what our maintenance practices are like and so on, we can reduce the planned downtime in addition to the unplanned downtime, and all the savings we get from that and all the increases in revenue, depending on the nature of your business, that's a big plus. Through that and additional techniques, we can reduce costs as well. And the idea with this cost reduction is not that we're going to say, well, hey, by making these changes, we're going to fire people or make those sort of arbitrary types of cost decisions. Just by seeking to improve reliability, you can reduce costs quite dramatically, in fact. Reduce the amount of waste that's going on now, and as a result of all of these things, reduce the number of safety incidents, so make the plant safer. There's no doubt that a reliable plant is a safer plant. And so, that's important for one obvious reason, hey, everyone wants to work in a safer plant, but also if you're trying to justify this to more senior management, and they might think, well, you're talking about spending money or performing work that you weren't performing before, so how are we going to do all of that? Well, some of these points are what you can use to help justify any of these improvements, and that safety one is usually one that gets people's attention. Particularly, more senior management, they say, yeah, I've got to reduce the number of safety incidents, and there's no doubt that reliability is a way to do that. Same way with environmental incidents. And then, of course, quality should be on everyone's mind, and of course more so in some plants than others, depending on the type of product or service you're providing. But we can definitely increase the quality of the products we're producing, have less waste, and by improving reliability. And of course, depending on your position in the world, but certainly from a senior management point of view, they are very interested in keeping shareholders happy, keeping the regulators happy, government institutions and so on, and improving reliability is a way to do that. And finally, employee satisfaction, which should be of interest to senior management and certainly should be of interest to you. But there's no doubt that it's a more fulfilling job role, I guess, if you're working in a plant that is more reliable and that the sorts of skills that you have can be employed to doing the best possible job rather than just dealing with the latest problem. If all you're doing is reacting to today's issues, then it's not as satisfying as if you can employ the highest quality work and see the plant develop and expand and so on. The question is, how do you do all of those things? And really it's a combination of sort of asset management and people management. There's a lot we could talk about on the asset management side, but this is all about managing the assets of the plant. And again, I'm emphasizing asset management for a couple of reasons. But again, if you have to try and go to management to get approval for any expenses, buying a vibration analyzer or doing, changing the way you handle lubricants or whatever it is. I mentioned safety and quality. Well, asset management should be something that they're very interested in. There is a new standard called ISO 55000. And ISO 55000, it's sort of like ISO 9000, whereas 9000 is all about quality, and a lot of companies got on board with that. ISO 55000 is about asset management. It's a way of sort of being able to say to your shareholders or the ownership of the company or the government regulators or whatever, to say, and to insurance companies, we are managing our assets properly. So those issues are important. They get the attention of senior management. But we do all of that by asset management, working closely with the people within the organisation, because if you don't do that, all of these things I talk about, even though I'll focus on a lot of technical issues in this presentation, it's all about people issues, the people who work on the machines, the people who design expansions to the plant and everything else. But we're going to do it through condition monitoring and condition improvement. So whatever type of equipment you've got, whatever it is, however it works, there's a lot you can do to improve the reliability of that equipment. So we're just going to take a quick look at from the condition monitoring side of things. We know failure happens, and no matter what we do, we're not here to say that you can totally avoid any failure of any sort. That would not be realistic. But you can avoid the majority of failures, and you can manage the ones that you can't avoid. And the good news is, from a condition monitoring point of view, the reason we're all here is that all that equipment is giving you lots and lots of warning signs as its condition starts to degrade. And this particular graph I'm about to show now, interactively, is called the PF curve. But the idea is that we start at a position where, the y-axis there is the condition of the equipment. So right now, there's my little motor there, and it's happy and it's operating defect-free. And hopefully, and this is not a given, but hopefully when we purchase the equipment, when we store that equipment, and then when we go to install the equipment, it's starting from that defect-free position. That is actually unlikely, to be honest. The way most people look at the design process, the procurement process, the transportation process, and everything else they'll talk about a little later, chances are you've already damaged the machine. It's already been harmed. There's already problems within the equipment before you're even starting to run it, let alone when you then run it. But we'll talk more about that later. But let's just say that, at some point we're running defect-free, but then at some point something happens. And we will go for a little period of time afterwards where we can't tell that there's a problem. But that problem could be because we've not aligned it properly, not balanced it properly. It's been damaged, the bearings have been damaged while they were stored on a shelf, while they were installed. The operators aren't operating it properly. I could go on and on and on and on, and I will later, about all the things we can do to the equipment to ultimately harm it. But we will go through a little period where we will find it hard to detect that failure has begun. But from that point on, we can say that the condition will be degraded. The condition will go down and down and down. And if we don't do anything about it, we'll get to a point where it will catastrophically fail if we did absolutely nothing. But we can actually identify a point just before that, some point before where we call it, it's functionally failed. And that F for functionally failed is the F in the PF interval. So at that point we can say, you know, that equipment is no longer able to perform the function it was intended to do. And that could be because of the pump, you know, performance characteristics. You know, we can look at a lot of examples, but it's no longer able to do its job. But it may actually be that it's seized and it's stopped or whatever. So the point is that it gives us all these warning signs beforehand. And one of the keys is that the earlier that we can detect this problem, the earlier we detect it, the lower is the risk of failure. The lower, therefore, is the risk of, you know, any safety incidents as a result, any environmental incident, and so on. But also, the cost of dealing with the problem is the lowest if we can detect it as early as possible. And the longer we leave it, by detecting that fault with different technologies, the risk of failure goes up. The cost associated with dealing with this problem goes up. We have less and less planning time to deal with it all. And again, the costs escalate, because if we're not detecting it until a late stage, then we do have to keep more parts in the stores, in inventory, to deal with that fact that we need to deal with this problem urgently. So that's what condition monitoring is about. Now, these little flags here, ultrasound, vibration, and so on, you know, I put them in a certain order. It's not necessarily that with every fault condition, ultrasound will pick it up first, and, you know, infrared will pick it up last, or something like that. You know, electrical, you'd use infrared. There's different types of failure modes, different type of equipment. Then there's different condition monitoring technologies as a result. And the challenge is we need to understand this sort of thing. You know, how much time is it from this point of potential failure, that's the P in the PF interval. You know, there's the P potential failure. How much time do we have between that point and functional failure? Because if that was a very short period of time, well, we need to be taking measurements very frequently in order to detect it so that we can respond. And that's why, for example, on big steam turbines and so on, we have protection systems that are watching every split second, because they can go from happy to destroyed very quickly. On the other hand, your normal motors and pumps and so on, rolling element bearing failures and that sort of thing, we have more time. But again, we need to be using the right technology, using that technology correctly, and taking our measurements frequently enough that we can detect that this failure has begun, and then we can deal with it. We can plan it, schedule it, and do replacement and so on, so that it doesn't interrupt production, or we have minimal interruption to production. We order the parts, do all those things which reduce the costs, reduce the impact. But as I'll talk about a bit later, what we'd really prefer to do is never have any of this happen at all. You know, it's great detecting this, but we'd really rather that this all happened 10 years in the future when some fault develops, rather than 10 months or 10 weeks after we install equipment. So anyway, let's have a quick talk about what all these telltale signs are. You know, how do we know that the problem exists? Now, I'll talk a bit more about vibration later, but the fact is that from within the machine, we get all sorts of telltale signs that a problem is developing, and it all depends on what the problem is. You know, we can sort of try and listen into the bearings, or listen into the rotor bars, or listen to the sort of the shaft, just the turning of the shaft. And as you can hear, you know, there's different frequencies, different amplitudes. Now, in reality, I'm not probing in and listening just to the bearing or just to the rotor bars or something like that. I'm not able to do that. I'm just listening to the motor overall. You know, as I'll mention in a moment, you know, we can look at it vertically and horizontally and axially because the machine's moving in that manner. We need to get the whole picture of it. But the different sounds that the machine makes, you know, we can hear some cavitation. Okay, most of your machines probably won't make that sound, but machine head, I couldn't resist. Okay, so the machine makes all these sounds, and all we've got to do is use our vibration analyzer to go and say, okay, let's listen to it here, because we can sense the vertical vibration, we can listen to it over here, and as long as we're collecting the right information, then we can tell. We separate all those sounds into what's happening with the rotor bars, the bearings, and everything else. And like I say, I'll elaborate on that in just a moment. So vibration is great for rotating machinery, but there's much more we can learn with other technologies. And the more technologies we use, we get a complete picture. You know, if you're trying to make a critical decision about what to do with a piece of equipment, you know, does it have a problem or not? You know, am I going to request that the bearings are replaced but there's nothing wrong with the bearings, or, you know, that it should be aligned or balanced or something like that? I mean, the most common reason a balanced job does not succeed is because the machine was never out of balance in the first place. You know, people see, oh, high vibration, balance it. It's like, yeah, but it's not out of balance. No, but it's got high vibration, balance it, you know. Anyway, it's just one of those things. So we need to understand the equipment and how it fails, and therefore use the technologies appropriately so that we get a proper warning of what's going on. So one of the things we can do is measure the temperature. And a simple way to do that is with this little spot radiometer. You know, we get the little laser beam and, you know, point it, and we sort of are able to measure the temperature, for example, in an electrical application. But with all of these technologies, you have to understand sort of, you know, the strengths of them and the weaknesses. You know, with something like this, you can sort of see this little cone there. Well, as you increase the distance, if you like, the cone gets wider. So what you're actually measuring is maybe not what you think. You're pointing it at this conductor, but it's actually taking the temperature from a wider area, and thus you're picking up something that's hot, even though you're pointing at something that's not. So anyone who uses one of these tools and thinks, oh, I'm you know, from the Wild West, slings it out and points it at a target a long way away, you know, they're dreaming. They're just not measuring what they think, even if they've got a steady hand and can keep that laser beam, you know, right on the target. So we use thermal imaging instead. And with a tool like this, hey, it's fantastic. You know, we can really get a much better picture of what's going on with the equipment and target problems. But thermal imaging is one of those technologies that is so attractive, you know, up front. You know, purchase it and they're getting cheaper and cheaper and cheaper. I think there's now something that's less than $500, even just a couple of $100. You can plug it into your iPhone and it looks like you're doing thermal imaging. Well, yeah, you're seeing something that's hot and something that's cold, but it's important with all of these technologies, and particularly with infrared, to actually understand what you are measuring and understand things like emissivity and other issues, the environmental conditions, understand how heat transfers from one point to another, understand what it actually means if something is hot. What is the root cause? What is it that needs to be repaired or dealt with? And that's the problem. With a lot of these technologies, you know, it's easy to buy it, point it, and jump to a conclusion, and next minute you're actually causing more harm than if you'd done nothing. That doesn't mean to say, you know, if you use it properly, hey, you can have fantastic results. You've got to understand what you're doing with it. There's lots of tests you can perform on electric motors. In addition to just taking vibration readings, we can examine the windings, the connectors. We can examine the supply of the voltage to the motor. Insulation, I forget whether I said that. So there's a lot of tests you can do that examine exactly what's happening with that motor, even detecting some of the mechanical properties of the motor through electrical tests. And those tests can be performed while the motor's offline, like while it's still in stores, and you can check that it's actually fit for purpose, and you can test it while it's operating as well. So there are lots of tests that's sort of more on the electrical testing techniques, looking at resistance, impedance, and these sorts of things. But it's amazing what you can learn. And again, it's all about avoiding those problems, avoiding the failure. But in a case like this, we are detecting problems that exist. We're not necessarily preventing the root cause of the problem itself. So the contamination issue, the lubrication issue is one of the most important that you can think about. I mean, every machine lives or dies by the lubricant that's operating inside. So whether it's simply, grease lubricating a bearing, is there enough grease in there? Is there too much grease? Is it contaminated? Is it the right grease? Have you mixed different types of greases? When you look at a gearbox, for example, and the lubricant within a gearbox, it is so important that it has the correct lubricant properties on the one hand. It's not contaminated with water, for example, or there's no particles. Someone's beeping. So there's a lot of things to think about, but there's condition monitoring tests for all of this that we can test to make sure the lubricant properties are okay, the viscosity is okay. We can check for contamination. We can check for particles that might harm the machine, and we can see whether there is wear occurring. So if there was any wear, we would see metal particles shearing off, and we can look at that. We can even look at the size and shape of those particles to see what condition the equipment is in. So, if you had some critical gearboxes, vibration analysis is great, but you'd be crazy if you're not doing this. Not only oil analysis, but wear particle analysis, looking at the particles themselves and learning from that. Really important. One of the issues with rolling element bearings and gears is that the clearances that we're talking about, between the rolling element itself and the raceway is less than 1 micron, less than a millionth of a metre. There's an awful lot happening way down there. The surfaces, even with your genuine SKF, NSK, etc. bearings, the genuine ones, not the counterfeit ones, they're not perfectly smooth. And so the lubricant is under tremendous pressure at that point. Tremendous pressure. So any problems with viscosity, any water contamination, all cause problems. Excuse me. And tiny little particles. Okay, for my animation I've made it look like a boulder, but we're talking about particles that are just a few microns in size. You can't hope to see those. You can't feel them in the oil. You can't see them in the lubricant or anything else. They are chewing up your machines, whether it's the bearings or the gearboxes. Those particles, they might cause just a little tiny bit of spot damage, but that damage spreads and harms your machine. Excuse me. And same way with gearboxes, those same particles get in there and damage the machine. So, we can do oil analysis tests to detect this stuff, and we can also try and prevent it. Ultrasound is another terrific tool. We can use ultrasound to detect a lot of mechanical issues with the machine. We can check if the bearing's greased correctly. We can use it while we're greasing, which I'll mention in a moment. But you can use it for electrical applications. We can use it to check for leaks and a wide range of applications. Now, most of these condition monitoring technologies, you'll hear in the practical sessions throughout the rest of the day. You'll be able to use the tool, actually, see how it works, see, what all the applications are. So you'll learn much more about all of these things. But the key is that each of these technologies have their strengths in certain areas, and they can be used to sort of back up other technologies. They have their different price points. They have their different skill set required, I guess. So, some of these tools you can put in the hands of operators as well. Get operator-driven reliability going, which is a great idea. I mentioned lubrication. Well, you can listen while you lubricate. As you're pumping the grease in, you can hear what effect that's having and hopefully pushing those surfaces apart. I mean, that's all great. Mind you, if you ever listen to the bearing and it sounds awful, that means you're not lubricating it properly, because it should never sound awful. But anyway, so there's a lot we can do with all of these different condition monitoring technologies. Now, just briefly, since this is the Vibrations Association, I'm going to talk a little bit more about vibration. Now, I know that, I see familiar faces here. This is back to the fundamentals, so I hope some people in the room want the fundamentals. But anyway, so just briefly, what we can do with vibration analysis is, let me switch to another little tool here. Okay, what I'm going to do is do that and do that. So what I've got here is an accelerometer which is used to help me measure vibration. So this sensor, hang on a sec. I already had it open, doesn't like that. That's the one I'm looking for. You go away. So this is the accelerometer. This is what we place on the machine to convert that vibration into an electrical signal. So what I've got it hooked up to my computer here, so that what I'm saying is what you're seeing. So this is the raw signal. This is the vibration in my throat. So if I hum, that was a pretty pure note, actually. How about that? Sign me up for the opera. I don't know what note it was, but it's a start. But anyway, so the sound the machine makes, it looks kind of ugly, but that is the raw time waveform. That's the raw starting point. It's just the electrical signal digitized, just like it was from a microphone. It's doing the same sort of thing. Now what I can do, though, is switch it so we can see the spectrum down below. Now while I'm talking, it looks a bit silly, but let's try that again. How do I do it? So that one peak is the frequency, and if I try and change the pitch, okay, that's about it. There you go, thank you, I'll take that, yep. You can see, the pitch go up, the frequency go up, and if I make a less pure sound, you see more peaks. So that's the basics of vibration analysis. You can get your certificates just outside the door. I can make that joke. Okay, so bottom line is, we're starting from that point where we get this signal, but obviously, the time waveform can be complicated, but can tell us an awful lot about what's happening inside the machine. The spectrum makes it simpler to understand. In really basic terms, the real basis of vibration is just that, with that motion, we get this simple harmonic motion, this simple sine wave. So as the shaft turns, it's one frequency which we can represent as one sine wave. If there's more vibration, then the amplitude of that goes up. If the machine was running faster, then the waves all get closer together. So, so if we speed it up, we see the little plunger being pushed in and out more quickly, and we get it changing, as you can see. We can have more amplitude. Okay, it starts to look a little bit unrealistic, but anyway. And of course, we're not using dial indicators. We've got sensors, which in essence do the same thing. In the case of a proximity probe, we are actually looking at the displacement between the tip of the probe and the shaft, or wherever we're pointing it. We can see that actual displacement, whereas the most common sensor we'll use is an accelerometer, and it's sensing the acceleration of the bearing housing itself. So you donk it on, the bearing housing is moving in response to everything that's happening in the machine. And that's one of the places where people can get caught out. There's a feeling that, well, no matter what happens anywhere in the machine, I'll be able to sense it if I just place it on the one bearing. Well, that's unfortunately not the case. It's also true that, if I had an unbalanced problem, I might move in this sort of circular motion, which creates vertical and horizontal vibration. I might have more horizontal vibration if the machine sort of found it easier to sway from side to side rather than up and down. But, in that case, measuring in the axial direction wouldn't tell me very much. But if I had angular misalignment, then there would be more axial vibration, and so we need to measure in 3 axes if we can. Somehow we need to get the whole story from the machine, the really high frequencies, the low frequencies, the works. So anyway, we put the sensor on the bearing, and we can then look at the individual frequencies. Now what I'm going to do just quickly is say, well, there's our primary source of vibration, just the shaft turning. And if you look at the animation, you can see, even the shaft's wobbling a little bit. So, there's the wobble of that grey shaft is my grey sine wave. And just to keep it simple, we'll focus on the fan. So, we're not putting a sensor on those fan blades. It's just that vibration, the thump, 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 as each blade goes by a reference point, if you like, is transmitted along the shaft through the bearing, and we sense it there. And, if there was hardly any vibration from that source, we wouldn't see much or more vibration. Likewise from the bearings. We'll keep it real simple for now, but we've got green vibration from the bearings. And if the bearings were in tip-top condition, we wouldn't see any vibration at that frequency. But with more, if there's more of a problem with the bearings, then we get more vibration. Bearings generate a few frequencies, and it's a bit more complicated than this. The point is, though, that what we actually measure is a combination of all 3, and it all sums together to make that more complicated. So what you're seeing there in red is sort of like what you were seeing from the accelerometer just a moment ago. So okay, that's all good, but what we'd like to do is really be able to say, okay, well, there's the grey vibration, the green vibration, and the orange vibration from those different sources. And that's what the FFT does, the fast Fourier transform, or the spectrum. And so there's our 3 sources. And so here I'm showing it in sort of 3 dimensions, if you like. I've got the time, the passage of time as the machine's rotating, and the amplitude, but here I have frequency. So if I made it slower, all those little sine waves, they drop in frequency, but they drop along that frequency axis. But anyway, if I now look at it from this standpoint, that is when I'm actually seeing the spectrum. That is the spectrum. And, we can switch to this mode. There's the vibration from the bearings, and as I say, there might not be any vibration. There might be a little bit of vibration. That's something we're going to watch for. If there was unbalance or a bent shaft or angular misalignment, there's a few reasons why. There's the vibration at the running speed, often called the 1x vibration. And there's our fan vibration. So the beauty of the spectrum is it's showing us all those little individual sine waves and everything else, and making it easier to understand, to see what's going on with the machine. Now we can also do time waveform analysis, where we do look at that raw signal, because sometimes the spectrum doesn't quite do it for us. Now this is a real simple sort of example, but if every now and again a cracked tooth went through the mesh, we get a whole lot of healthy meshes, as the good teeth are all banging into each other, if you like, or rolling across each other. But when that bad tooth goes by, we get the spike in vibration or a change. And a spectrum of that is it does not give us a good view of what's happening. But the time waveform, I can look at that and say, I know exactly what's going on. And here's a real example. So there's, the gears there, and you can see it on both sides, obviously, and you can see the damaged area just here. And because there is that damage, when that goes through the mesh, we see this spike. So this vibration, this low amplitude vibration in here, is the normal vibration from the gear. That's what it should always look like. When the bad tooth or teeth go through, we get this big spike. So again, we can try and see that through a spectrum. The time waveform is a great tool. It needs to be set up properly so we can see it, but this would, show us. If you looked at a time, some people are scared off by time waveforms. Oh, they're complicated. And I look at a lot of time waveforms that look like this. Well, if you look at a time waveform that looks like that, then that's telling you that there's nothing the time waveform, when collected properly, is telling you. If you see a time waveform, it's just a whole lot of blue like that. that just means go look at the spectrum. That is actually that same gearbox when it's healthy. And okay, it looks a bit jaggedy and so on, but that's this stuff in here, actually. Anyway, so there's also a technique we can use, phase analysis. Phase helps me understand the motion. So the spectrum split out all the frequencies. You know, there's the 1x peak and the 10x because I've got 10 blades on the fan and so on. So that's good. Time waveform shows me the nasty things that are happening, the impacting in the bearings when the bearings are damaged, the impact on the gears. But from a vibration analysis point of view, it's often very helpful to understand the machine as a whole. So, you know, before I sort of have this motion, like unbalance. Well, knowing that it's this sort of motion tells me something. Now, you might think, oh, don't all machines sort of rotate like that? Well, in truth, if I was misaligned, I would move in more of sort of a tight, maybe even a figure eight, but it's more in one plane than another. Because of the way the machine's been aligned, it's hard for the machine to move in that circular motion. It moves differently. And for a variety of reasons, when we look at all these fault conditions there are different forces involved, which make the machine actually do this, which make it do that, which make it move in very different ways. And phase enables us to understand that motion. It lets us visualize the vibration. So, one way to do it is we put the vibration sensor on the bearing as normal, but we're doing phase analysis. We can see if it's that circular motion. We can see if it's pushing, pulling, bouncing, swaying, rocking, twisting. We can learn all about that and relate that back to what the machine's actually doing. What is actually wrong with the machine? What do I have to fix? How quickly do I have to fix it? We can use strobes as well. Strobes are a great tool, and there's a lot of different ways we can use them. But, you know, if the machine's running, you might like to be able to slow it down and see what's actually happening. But a strobe flashes when you've set it up properly, once per revolution, and we see what's happening. And we can actually do phase analysis with that. We can put a sensor on, and as we move the sensor, which is synchronizing and firing the strobe, we can see things that way. There's a lot more I could tell you about how you can use strobes in this fashion, but just be aware that they are a very helpful tool. They can help you identify, you know, if something's rattling or vibrating. In this particular example, there's two belts, and one of them's flapping. So, okay, it's flapping a lot, just for the sake of this animation. If we turn on the strobe, I've got it firing at the running speed, and it happens that the belts are flapping back and forward right at the running speed. So flap, flap, flap. But because we're flashing at the running speed, we don't see the motion. So with the strobe, we can just detune it a little bit, and so we've just got it firing at a different rate, and now we see the belt flapping. We can see that one belt's okay, and the other belt's flapping. Very easy test to perform. You know, we can change the flash rate and we can stop the belt itself. And we can see what's going on with the belt. You know, so now you can see the little yellow marks on the belt aren't moving. About there. There you go. Anyway, lots you can do with the strobe. It's a very useful tool. So just very quickly, you know, some of the common fault conditions, you know, if we start from the position of a spectrum, you know, a normal spectrum is going to have a few peaks in it. It can be more complicated than what I've been showing. But basically with unbalance, for example, we expect that peak at the turning speed, the once per revolution speed, to go up in amplitude. If there was misalignment, well, it depends on the type of misalignment and all of that, and I'll mention a bit more in a second, but we'll see a change in that vibration. You know, rotating looseness, we get lots of peaks called harmonics. And because of the impacting, the bottom of the graph, the noise floor, can lift up. And these are all telltale signs that we can look for. You know, when bearings start to fail, we see their magic frequency. This is for damage on the outer race, but we get these harmonics. And there's lots we could talk about with each of those. And I think part of the key to all of this is actually understanding what the machine is going through when these fault conditions exist. So a simple one, like static unbalance, you know, we've got that motion which you've seen a few times, and there it is animated. So now you can sort of visualize, well, you know, this is moving in a circular motion. What does that tell me from a phase point of view? Between vertical and horizontal, that would be 90 degrees. I've got my sensors 90 degrees apart. The phase should be 90 degrees apart. If I put sensors at either end, that's all moving up and down together, so they would be in phase either end. And there's all sorts of things we can do depending on the type of machine. We still see, in this case, with dynamic unbalance, we get a different phase relationship end to end. So I have to do a two-plane balance now, but I still get that 90-degree rule working. And so we can do all of our vibration analysis, we can look at charts, but if you understand the machine and understand how the spectrum is going to change, then when you see the spectrum, you'll know what's going on and whether you perhaps need to look at phase or time waveforms as well. Misalignment, you know, I mean, this is pretty exaggerated, but if we were to unbolt it, fly it in space and let it vibrate, well, we might see a motion like that. And you know, this is the motion that how it wants to move, but you can see a phase relationship there. You can see that it's going to generate certain frequencies, but either side of the coupling, it's moving opposite each other. So there's a phase relationship. Of course, when we bolt it down, we're going to chew up the bearings and the seals and everything else, and that's why we don't want to leave the machine misaligned. Angular misalignment, different, and you're probably going to have both, but now it's more of an axial vibration. It's going to want to move axially. You know, if we closed up that coupling, it's pulling like this. And without going into all the details, you know, with misalignment, we can detect it through the spectrum. More complicated than what I'm showing here, but we can detect it. We can tell what's going on, we therefore know what we have to fix. Bearings, we're very fortunate with rolling element bearings because they give us some very unique telltale signals. You know, if the fault is on the outer race, then there's just sort of one impact as each ball goes past, and the force of the impact is the same each time. Whereas in this case, if the damage is on the inner race, as the shaft turns, we have those impacts, but the force of the impact in the load zone is much higher than out of the load zone. So that changes the vibration. We don't need to go into it now, but that changes the vibration which we can detect. We can see it in our time waveform, we can see it in our spectrum, we know exactly what's going on. Same as if the rolling element itself is damaged. And of course we might have a combination of all of these, but if you look closely at these animations, you can see that that is a different rate or frequency to that. That's occurring more frequently, and this is somewhere in between. So, you know, you can detect all these things. We can use techniques that detect the stress waves and all of that. We can get a very early warning that the bearing has a problem. And so very quickly, just to sort of prove that it worked, you know, here is a spectrum from a machine with a bearing that has a problem. And it's just, you know, there are these clear peaks that indicate that a fault exists. You know, that was the damage on the bearing. And, you know, there I'm just seeing these harmonics, as they're called, of the frequency that is related to that, the ball pass outer race frequency. And so we get simple harmonics in that case. In this particular case, there was inner race damage, and you can see that, you know, over a period of time, the vibration level increased and then, well, came down when they fixed it. The time waveform changed, as you can see there on the right. But if you look closely at the spectrum at the top, we've got more peaks, and it happens that we've got sidebands. That tells me the damage is on the inner race instead. And when you look at the bearing afterwards, you can see those black lines? That was the damage that was detected. Now the key with all of this is never to just detect that the problem exists and replace the bearing and say my job's done. Your job's not done, because you've got to ask the question, why did that happen? You know, why was the bearing damaged? Because if we don't ask that question and fix the root cause, well, we'll just be back here after a little while fixing the same problem. So this could have come about for a couple of reasons, but the most likely reason is something called false Brinelling. So you've got a pump sitting in standby and it's vibrating the whole time. It's not operating, just vibrating. And the rollers are chipping away at that inner race and the outer race. We run the machine and lo and behold, we get this fault condition. So if you do nothing, then this is just going to happen again. We'll be replacing the bearing again. And how many times have you seen in the plant, oh, that machine, yeah, we have to replace the bearing quite frequently. Yeah, but why? And of course, there's other reasons for bearing faults, and you have to understand what's going on. This is a different sort of a problem. This is from a paper machine on DC drive. You can see all those little peaks that are all sort of concentrated up the higher frequency end, and you know, it's a telltale sign of something called EDM, electro-discharge machining. But it's basic, and that's what the bearing would look like. So again, if you pull the bearing out and you look at the bearing, it's telling you a story. It's saying, this is why I failed. This is what happened. So this is what you have to avoid happening again. If you just scrap the bearing, how would you ever know? You just think the job's done. Okay, I've replaced the bearing, job's done. Well, it's not done. And this is why we're trying to improve reliability by eliminating these root causes. In this case, and you can see the little spark at the top and bottom of the bearing, there is current flowing through the bearings. And it leaves that etching on the bearing, and it'll eventually fail. This is a slightly different type of case. This is a big exhauster in a steel mill in India. And the story here was that the person sent me an email and said, oh, you know, the vibrations changed, but I don't quite see what's going on. And it was just, you know, a spectrum, and you can see the peaks. There's 3 axes. You can see there's some fairly clean-looking peaks, but you notice that the peaks kind of look broad. Now, you may not be familiar enough, but they kind of look a bit fat. And he's saying, why is it so? So I asked him, take a higher resolution measurement. It's kind of like taking a picture. If I took my iPhone 1 and took a picture of you from here versus an iPhone 6, you know, with many, many more megapixels. In the iPhone 6, I can see much more detail. Well, it's the same way with vibration measurements. But in this case, when we took a higher resolution measurement, we saw that around the peaks, there were actually these side bands. And that is a classic sign of broken rotor bars or cracked end rings or something like that. So I said, well, that's what the problem is. And so they took the machine out, or the motor, blah, blah, blah. And they, as you can see there, all the marks around there were quite a few damaged areas, but that's what they saw. So that problem made the spectrum change in that way, and we were able to detect it. And before they had a catastrophic failure, before they had a production issue or anything else, you know, they have spares with these. They were able to, you know, manage the process and deal with it. So condition monitoring is great. Fault detection. We can plan our maintenance so much better. We can avoid the secondary damage. So we rather than the bearing seizing and perhaps damaging the shaft or anything else, we avoid that. We can reduce parts inventory. You know, if you're confident that you're going to detect problems, then you can say, well, you know, I don't need to keep all these spares on hand, which is costing you money. They might be degrading. It's amazing how much that can cost your company just keeping, you know, all these spares in inventory. Whereas you can, if you've got this under control, you can make sure you've got availability of these sorts of spares from the vendor and let them keep them on their shelf, basically. But anyway, we can do lots of things. We have the fewer safety incidents. But the question that I'll come back to that I mentioned at the beginning is, you know, are we actually improving reliability? So yes, you know, with the shredder, with the exhaust fan in India and the other examples, we provided a benefit. We did provide a benefit. And standing back far enough, we can say, well, the plant production is more reliable now because we're able to deal with these problems more efficiently and more effectively. And that is a good thing. But when you get down to the machine level, we are still therefore making repairs, we're still having to deal with these problems that for the most part shouldn't exist. And so therefore we're not really improving reliability by monitoring the condition of equipment, unless we are monitoring the root causes of the problem and avoiding those. So that's what we should be doing from a condition monitoring point of view. If we can detect the little bit of misalignment, the unbalance, the lubrication issues and all of that, then we can deal with the root cause before it turns into a bearing fault or a seal failure or something else. If we can detect those root causes and do something about them, then we avoid what is the true secondary problem, and that is the bearing failing. So that's all good. And the idea, therefore, if we go back to our PF interval, is what we really want to do is just stay in this mode. Now, I think Bob Kraft is going to be talking about this tomorrow, so I won't dwell any further on this particular point. But we just want this machine to run for as long as possible, trouble-free. But the question is, why do they fail? You have to ask that question. You have to ask the question, why is our equipment failing? Now, perhaps in some of your minds, there'll be all kinds of reasons, maybe even excuses. Oh, our industry is crap. We've got an old plant. Oh, management this. Oh, procurement that. The reliability engineers don't know. Like there can be all sorts of reasons and excuses and everything else. And they may seem legitimate, but all I can say, one of the luxuries of my role with my company and all that sort of stuff is we see companies all over the world, from the oldest you can imagine to the newest, to the dirtiest industries to the cleanest, and so many of these problems occur and exist in exactly the same way in all of those. As in, I've seen incredibly old plants have tremendous reliability, or demonstrate incredible reliability. And I've seen new plants that are terrible. Steel mills that do really well and cleaner, simpler industries do poorly. It's all about the people and the management. We can talk about the tools that will help us, detecting the problems and doing alignment better and all of that. But, I won't ask for a show of hands, but I know laser alignment, fantastic tool, must use it. But how many people have purchased it and it's not been used properly? They didn't even have any tolerances. And the person doing the alignment, if they even use it because maybe it's a bit intimidating and they'll just go back to their older techniques, no one's watching, I'll just do it that way. Or they're doing the laser alignment and it's telling them to put this shim that's about this thin. It's like, as if that's going to make a difference to this machine. I'm not going to muck around putting another shim under this foot. I'm done. It's got to be good enough. It's that appreciation. You can't just throw tools and technologies at this problem and think it's going to fix itself. Until everyone understands what reliability is about, how they all benefit by working in a plant that is more reliable. And unless everyone can ask themselves, what can I do to contribute to the reliability improvement initiative? Well, then it's just not going to work. You need senior management on board saying, yes, safety is important, the environment's important, quality is important, and reliability is important. It's got to be up there with the edict of the company. Reliability has to be up there. And all the way down to the plant floor. Operators. This isn't a maintenance issue. This is not a maintenance issue. There's a lot that maintenance people can do to improve reliability, but reliability is not the maintenance department's fault. Now, you can say, well, this is where we are now in our particular plant, and perhaps this is where we'd like to be. And perhaps along that path, there's a lot that the maintenance department can do. And maybe that's the place to start, but it's not the place to end. Because so much happens with the design and procurement, so much happens with the way the equipment's operated, with the inventory management and everything else. It's a much bigger picture. And until that's appreciated by everyone, and everyone really understands, why reliability needs to improve and how that benefits me, what's in it for me. People have to answer that question before they want to change. But until everyone understands that and contributes to the change won't occur. And this is, for me, a bigger issue than all the technology that I've talked about so far. Because unless people change, all these problems will just reoccur. And you can throw some technology at it and you can have some success, you can have some improvement. But if you're really aiming for a properly reliable plant, then these are the sorts of things that have to happen. Now, some of you may even be thinking, oh yeah, but you haven't met the guys at my plant, they don't want to contribute, they like the overtime and blah, blah, blah. All I can say is I've seen it and heard it 1,000 times. But there are so many plants out there that give people the opportunity to change, and they usually grab onto it with both hands. Because most people don't actually like dealing with the crap that keeps occurring when there's failure. They don't like being dragged out in the middle of the night or on the weekends. They don't like the safety issues. They don't like the economic threat that seems to hover over the plant and all of those other things. They don't like that. But it's like anything else. If you just point to a person and say, you're going to do your bearing installations better, or if you point the finger and blame and all of that and think that's going to solve it, you're kidding yourself, of course. On the other hand, if you say, why do you think there's a reliability issue? Well, we do this. Okay, let's fix that. It was a great idea, great suggestion. Can you contribute? Yeah, I'll help, And everyone, this fella here, he came up with this idea and we've made an improvement. When people contribute and get positive feedback from these sorts of changes, makes the world the difference. Just makes the world the difference. The trouble is that in this world we have, often engineers, but other people as well, who want to control things a bit too much. They think they have all the answers. So they're going to squirrel themselves away in a room and come up with an RCM project or something like that. Try to come up with all the answers, and then they'll tell everyone else. Well, if it ever gets that far, RCM projects often don't ever get out of the room. But if they do, and they start telling people what they've got to do to change, like anything, you have some improvements, but the minute that person gets promoted to a point where they can't do any more damage, or they leave the company, or they become a consultant or whatever, things just slip right back because no one ever believed it, no one ever really understood it, no one felt a part of it. So I would just say that, they are the issues that you need to deal with. Because why do the bearings fail? We kill them. Now, that's a quote from Rod Bennett. It's a great one, so I'll reuse it. It's just the fact. You can go to the bearing suppliers out there and say, well, how long should these bearings last? A lot longer than they are lasting is the answer. And it's nothing to do with the bearing supplier, unless you're buying counterfeit. It's how they're being aligned and operated and all the rest of it. Because if you think about it in terms of the bearing, that bearing, as I've mentioned, operates under tremendous strain. It's designed to manage it, but once you overload it with unbalance or resonance or misalignment, or you don't lubricate it properly, then it fatigues, and it might fatigue down, subsurface at first and break through to the surface. But all of those issues cause these bearings to fail. And whether it's that contamination that we looked at in the bearings or gears, whether it's unbalance, whether it's the misalignment, whether it's the bearings being cocked on the shaft, or it's been hammered into place and scored the surface, or it's cocked in the housing, or it's misaligned, or we've got EDM, or we've got false Brinelling, and we could keep going on and on and on and on with all the possibilities. The fact is that, for the most part, condition monitoring, most people's condition monitoring program is all about detecting that. Oh, we have a problem. And aren't I clever for detecting that this exists? So now we're going to plan to replace that bearing. You know, what condition monitoring can't do is magically fix the bearing. You know, we can't do that. We can't fix it once it's damaged. Now we're reacting. You know, we can put a fancy name, you know, condition-based maintenance or whatever, on what we do. But the fact is that a lot of people's condition monitoring programs are really just reactive maintenance. It's just that instead of hearing that the bearing's screaming or detecting it a bit earlier with the screwdriver, we're just detecting it earlier with our vibration analyzer, which is all good. You know, that's a good thing, but it's reactive maintenance. It's like, oh, here comes the bad news from the vibration guys or the oil analysis guys or whatever. We've got a problem we have to deal with. Well, we should be getting ahead of the curve and not waiting for the problems. And I'll actually skip this little bit. The real key, I'm running up against time, the real key is to take a big picture view of all of this. So there's our precious machine. And our business relies on that machine running and running and running. We just want to keep it running. We want to take care of it. You know, I've got it sitting on a pillow there. So the first thing we have to do is put a force field around the plant and say all of those problems that are coming from suppliers and vendors and contractors and all of that, stay out. Just don't let them in. Whether it's, now I say unreliable suppliers. I don't mean suppliers that don't deliver on time. I mean suppliers who, unbeknownst to you, sell you bearings or motors or pumps or whatever else that already are defective or they're not properly rated or whatever. We've got cheap spares that don't do the job. It's not being transported properly, or we've got contractors doing balance jobs or rewind jobs or whatever, and they're not doing a good job for you, and you don't know. You know, you're not specifying how it should be done. You're not specifying what a good job means, and you're not testing it with acceptance testing when it comes in. So if we do all that and we take care of the design processes as well, if we could take care of all these things and use acceptance testing to make sure nothing gets in that shouldn't, what gets into the plant will provide you a higher level of reliability. The inherent reliability will be higher. But then the question is, what would we do to it? Well, we need to put a force field around the machine. And we need to look at, you know, are we buying lubricant and then contaminating it? Because we leave it outside. Oh, there's so many ways you can contaminate your lubricant. I guarantee that if you're not focused on this particular issue, you're putting contaminated lubricant into your machine, thinking it's good and clean. Well, it's not. We're using parts that are already damaged because they've been sitting on the shelf, or they've vibrated on the shelf, or they've been contaminated on the shelf, or whatever. We're not using optimal installation practices, and like alignment and the way the bearing's installed and so on. And operating procedures, you know, maintenance and operation need to work together. They need to understand that they're part of the problem when it comes to reliability, and therefore they need to be part of the solution. Sounds very cliched, but it's just, that's just the way it is. We do PMs that actually harm the machine, or that are just totally useless and we could be using our time better. So many of the preventive maintenance tasks are actually generating maintenance issues. That wasn't, I don't think, how it was meant to be, you know, particularly intrusive inspections. So if we can avoid all those problems, this is where we are improving reliability. You know, so far, other than the acceptance testing part, we're not worrying about condition monitoring and all of that. Condition monitoring is sort of like the last line of defense. If everyone else did their job properly, then the condition monitoring guys would probably have a bit of a boring job. I took more measurements today, didn't find any problems again. Jeez. Look, those good old days where I used to find bearing faults all the time, you know. The good old days. We need to give big hammers back to the guys installing the bearings. My job's getting too boring. Kidding, of course. But, you know, from an acceptance testing point of view, we use condition monitoring skills. when the alignment job's done, when the bearings are installed, when the machine's being commissioned, the condition monitoring guys check the machine and make sure it's all good. And then, of course, we keep monitoring the machine. We keep making sure it's clean and adjusted and all those things to make sure that it will remain reliable. So if we understand, how the machines fail, if we understand all those common root causes, and we can look for the unique ones from your plant, then we've got a chance of having a reliable plant. And we still use condition monitoring, because things still fail, things still slip through the cracks. And when we do find a problem, we use root cause failure analysis to find out why it slipped through the cracks. So, we all know that the breakdowns can be frustrating and costly and everything else. But fortunately, there is a solution. We can monitor the equipment to find these problems early, but what we really want to do is improve the condition. Use our monitoring techniques to look for the root causes, the unbalance, the misalignment, the contaminated lubricant, and deal with that. But step further out and make sure that those problems don't happen in the first place. And we can all be happy. Thank you. That's my presentation. Any questions? Do we have time for questions?
We've got a couple of minutes, 1 minute. Is there any questions?
Well, if no one, if you've got a question, please ask. Otherwise, I'll be around. And the rest of today, you're going to be meeting with people talking about these individual topics. And they can go into more depth with you. You can actually see the tools being used, see how they work, understand the philosophy behind them and the whole thing. So that'll be a good time to get some discussion going.
Thank you, Jason. Yeah, I like what you told us about reliability and cost savings, and how we tend to like in this country, in Australia, to lay people off to save money. Of course, we all know that the minute you suggest that we're going to lay some people off, your reliability goes.
Yeah,
Morale,
makes the problem worse.
And it makes the problem worse. So at least we're educated.
Yep.
So anyway, if you'd like to hear more of Jason, he'll be the guy singing karaoke in the bar tonight with an accelerometer.